so we're in section 13.6. So we're talking about directional derivatives. And the gradient. So we spent a little time a couple of sections ago talking about the partial derivatives of a multivariable function. And we said that the partial derivatives gave us the rate of change of the function in the x direction when we held y constant, or in the y direction when we held x constant. What we're interested in today is coming up with a way of finding the rate of change of our function in any arbitrary direction, not just in the x direction or in the y direction. So we want the rate of change in any direction. So what we're going to do is, our goal is we want to find the rate of change. So we want the rate of change of, we're going to say z is some function of x and y, in the direction of an arbitrary unit vector. We're going to just pick any direction, and we're going to call our unit vector, u is going to be the vector AB. So some arbitrary unit vector in the plane, and we want the rate of change of the function in that direction. And we're saying that our magnitude of u is 1, and we're interested in this. We want to be able to find this rate of change at any particular point. So we're going to say at some point x0, y0. So let's draw a little picture of our surface and our vector and start developing this idea. So there are our coordinate axes, z, x and y. And here's our surface, our surface up here. And we're going to say that we know at this particular point, this is our x0, y0, f of x0, y0. And we want to move along this surface to some other point. And our z value is going to be f of xz. And we're moving in the direction, I'm going down here into the plane now. We're moving in the direction of this unit vector. So here's my unit vector in the plane. So we're moving along the surface in the direction of that unit vector. So there's our unit vector. And we have this point in the plane that's the initial point of our unit vector, so we're going to call that p x0, y0. And we move along here, and I'm going to drop that down to the plane. And in the plane, this is going to be point Q, and we'll call this xy. And this should be xy here. So we're moving along our surface in the direction of that unit vector. So our average rate of change here, we're going to start with that. Our average rate of change is just the change in the function divided by the magnitude of this vector PQ. That's our average rate of change of our function as we move in that distance. So it's going to be f of x y minus f of x0 y0 divided by the magnitude of that vector PQ. That's going to be our average rate of change. So we're thinking just like we did with a function of one variable, we found our average rate of change, and we're going to use this average rate of change to get to our instantaneous rate of change. So our instantaneous rate of change, the easiest way to get an instantaneous rate of change here is just to take the limit as the magnitude of PQ approaches 0. So our instantaneous rate of change is going to be this quantity, but as the magnitude of our vector, PQ, as this distance changes just by a very small amount. So we get this limit. And we're dividing again by the magnitude. So there's our instantaneous rate of change. As we're moving along the surface in the direction of this unit vector at point x0, y0. We're going to call this limit the directional derivative. It's the rate of change of our function in the direction of vector u. So this is the directional derivative of f at x0, y0, just to add our details in here, in the direction of u. So we've done this several times over the course of the year, where we come up with a definition, we come up with what we're going to call this thing, but this doesn't help us calculate this directional derivative. We want to be able to do something with this rate of change. This limit doesn't really help us. So we need to do a little more work to get to something that we can actually use. It's actually going to be helpful for us. So this limit tells us what we're talking about. We want to get to somewhere where we can actually use something. Now, when we write this, the notation for this directional derivative, we write capital D, and there's our vector u, the directional derivative in the direction of u of f at x0, y0. So this is our directional derivative of f in the direction of vector u. That's our notation for directional derivative. So now we need a way to calculate this derivative. This is like we did in single variable calculus, where we defined our derivative as a limit as delta x approaches 0. Doesn't really help us calculate. So we're going to do a few steps to help us calculate this directional derivative. All right. So questions on what we're talking about so far? Okay. So we're going to say that we know that vector PQ is parallel to our unit vector. We're moving in the direction of that unit vector. So we can write so PQ is some scalar multiple of our unit vector, where h is some scalar. So we said that u was the vector AB. So PQ is going to be the vector HA, HB, for some scalar h. And then we can say that as we move along that vector, that x, our arbitrary point x, is going to be x0 plus HA, and y equals y0 plus HB. So this is our we were writing parametric, these would be our parametric equations for the line in the direction of vector u. And the distance we travel from x0, y0 to our point xy is the scalar h. That tells us how far we're going along that vector. So what we're doing here is kind of a, not really a sneaky way, but we're parameterizing that distance we're traveling along vector PQ in terms of its arc length. So I said that arc length, parameterizing in terms of the arc length was going to be an important idea. That's really what we're doing here. H is our arc length. That's telling us how far we're traveling. So we're parameterizing that distance, that vector, in terms of its arc length. So we're going to substitute this into our limit that we said was our directional derivative. So the limit as the magnitude of PQ approaches 0, our directional derivative f of xy minus f of x0, y0 over this magnitude of PQ, we can rewrite this will be a little more useful, is going to be the limit as h approaches 0. As h approaches 0, we're traveling less distance along that vector of f of x0 plus ha, y0 plus hb, minus f of xy over h. So this is how this limit, so this is our directional derivative. We're going to define this second limit as our directional derivative. So this is going to be our definition of the directional derivative. We're going to use this as our definition. So this first limit was our idea. This is what the directional derivative is, this instantaneous rate of change. We're going to define the directional derivative as this quantity. So this is like our definition of the derivative with a single variable function, the limit x plus delta x, etc. And we can calculate our limits, our derivatives using this limit. It's kind of tedious, takes a lot of algebra to come up with this limit to where we can manipulate it. So we're still going to do some more work with this. But this is our definition of the directional derivative. We're taking the limit as the distance we travel along that in the direction of that unit vector approaches 0, the rate of change of our function divided by that distance that we travel. Now if our unit vector is I hat or j hat, this directional derivative becomes our definition of a partial derivative. So the partial derivatives are a special case of the directional derivative. Partial derivatives are directional derivatives in the x direction, directional derivative in the y direction. So if this vector, if our unit vector is the I hat vector or the j hat vector, then our directional derivative becomes what we did with our partial derivative. So this limit, a better idea of what the directional derivative is, but it's still not easy to calculate. We want something that's going to be easy to calculate. So we've just rewritten this limit in a way that's a little easier to work with. This limit's a little easier to work with than this limit, but it's still not easy to calculate. So we want something like the power rule. For taking derivatives of a single variable function, we want something that's easy to work with like the power rule. So we're going to do that by using the chain rule. So we just talked about the chain rule a couple of days ago. So we're going to use a chain rule to come up with a way to calculate our directional derivative. So questions so far? So taking a little bit of time to develop this because it's kind of important to understand what we're talking about. All right, so we want a way to calculate this. We're going to use a chain rule. So we've said, just to recap, we have z equals f of xy, and x we said was x0 plus ha, and y equals y0 plus hb. Hello, Luis. I'll just go to your class. Yeah. We're going to use a chain rule. We want to find the partial of f with respect to h, the rate of change of our function with respect to h. And we want to take the limit as h approaches 0. So by the chain rule, this rate of change, this is going to give us our directional derivative when we take the limit. Taking the derivative of f with respect to h, and we're going to take the limit as h approaches 0. This is going to be the partial of f with respect to x times dx dh plus the partial of f with respect to y times dy dh. And I can write this, we can also write this as f sub x xy times a plus f sub y at a point xy times b, because dx dh is a and dy dh is b. Now we want the limit. We want the limit as h approaches 0. So at our point, at x equals x0, y equals y0, we're letting h become 0. We're taking the limit as h becomes 0. We're going to say that df dh that's going to be our directional derivative of f at x0, y0 is going to be the partial with respect to x at our point times a plus the partial with respect to y at our point times b. And I'm going to put in parentheses h is approaching 0 at our point. This is the formula that we're going to use to calculate our directional derivative, because we know how to take partial derivatives with respect to x, we know how to take partial derivatives with respect to y. So that gets us around this limit. So we've turned the directional derivative from this idea of a limit into something that involves partial derivatives. And the kind of the bridge that helped us do that was the chain rule. All right, so let's think about this quantity for a second. So this is the quantity that we're going to calculate our directional derivative with. So we have this quantity that is this partial with respect to x, so something that involves our x variable times the x component of our unit vector, plus the partial with respect to y, something that involves the y component of our function, times the y component of our unit vector. What does this quantity look like? What is the form of that quantity? What other quantity have we been working with that involves an x component times an x component plus a y component times a y component? A dot product. This looks like a dot product. So our partial derivative, our formula for calculating the partial derivative, looks like a dot product. So we're going to say, I'm going to rewrite this as a dot product. So the directional derivative in the direction of u at x0, y0 is going to be the dot product of this vector f sub x, f sub y, with our unit vector av. And I could also write that as the partial of f with respect to x, partial of f, just as a reminder, with respect to y. So we can think of this directional derivative as a dot product. And we have this strange vector here that involves these partial derivatives as one part of our dot product. This quantity, this vector that has these partial derivatives, that involve these partial derivatives, comes up so often, and this idea of a directional derivative comes up so often, that we give this quantity its own symbol. So we have our directional derivative. The directional derivative is this quantity. Partial derivative with respect to x times the x component of our unit vector. Partial derivative with respect to y component of our unit vector. We recognize it looks like a dot product. So this quantity comes up so often that we're going to give it its own name, its own symbol, and we'll do some more operations. So we're going to define another definition. Define the gradient vector. And this idea of this gradient vector is kind of the important one. Directional derivative is important. The gradient vector we'll use a lot. So the gradient vector for some function z equals f of xy, we're going to call it del f. So we get this upside down triangle. This symbol is called del. And del f is this vector that is the partial derivatives. Plus def dy I hat. And if we had a three-dimensional surface, if we had w equals f of xyz, we could add a third component. Which should be df dy I hat. Or sorry, j hat. J hat, there we go. Z hat, there we go. K hat. There we go. Z, K. So this, if we had a three-dimensional surface, this would be our gradient vector. So we call this del f. Del is what we call an operator. Because this gradient vector doesn't have any meaning on its own. The partial of f with respect to x I hat plus the partial of f with respect to y j hat, that doesn't have any meaning on its own. It has to operate on something to have a meaning. We have to take the partial derivative of something. So we have to operate on a function in order for it to have a meaning. It has to operate on a function, and eventually we'll have it operate on another vector. So we have this operator, this gradient operator, that is these partial derivatives. And this is how we're going to calculate our directional derivative. We can use the gradient operator, and we'll do the gradient of our function at a particular point, and we'll take the dot product of that with a unit vector, and that will give us our directional derivative in the direction of our unit vector. We'll do an example or two in just a second. So a couple of other notations you'll see for the gradient for del f. You will see del f. You'll also see grad f. So you'll see both of those notations. So using this gradient vector, we can write our directional derivative in very compact form. Our directional derivative in the direction of u of f of xy becomes del f at xy dot u. And we need our magnitude of our unit vector, or magnitude of our vector, to be 1. So this is our compact form for writing our directional derivative. We take the gradient of our function and take the dot product with our unit vector. And a couple of things, we'll talk about some properties of the gradient in just a second after we do some examples. The gradient of a function of x and y gives us a vector in the plane, not in space. So it gives us a vector in the plane. We can think of the gradient vector as kind of as a compass direction. It gives us the direction in the xy plane. It's not a vector in space. All right. So taking a little while to develop this idea of a directional derivative. We want the instantaneous rate of change of our function in the direction of an arbitrary unit vector. We brought it to the idea of a limit, and then we looked at the form that our limit took once we applied the chain rule to our function, and we came up with this idea of this gradient vector. We'll spend a little time on the gradient vector. We'll work with it today. We'll do a little more work with it next week. And it'll come up quite frequently in the rest of the chapter. So let's use a gradient vector. Let's use a gradient vector to calculate a directional derivative. Let's do an example or two. All right, questions on what we've talked about so far. So for now, the entire point of what we've done is so that we can calculate the rate of change of a function in the direction of a particular unit vector in the plane. All right, so let's say we have g of xy equals the square root of x squared plus y squared. And let's say we have a vector 3i minus 4j. And our point is 3, 4. Questions, guys? We good? Everybody good? So what we want here, here's our function. We want the directional derivative. In the direction of v. At the point. So we want to know at the point 3, 4, what is the rate of change of the function in the direction of the vector 3i minus 4j. So the way we're going to calculate our directional derivative is going to be del g dot, and we need to take our dot product with a unit vector. We want a unit vector in the direction that we're moving. So v over the length of v. That's going to give us our directional derivative. So let's calculate our gradient of g, so del g. Del g is, just as a reminder, dg dx I hat plus the partial of g with respect to y, j hat. So let's calculate these partial derivatives. What's the partial of g with respect to x going to be? I'll get us started. I hat. So what's a partial of this with respect to x? We've got to use the chain rule. So what do we get? 1/2 square root of, or 1/2 x squared plus y squared to the what power? Negative 1/2. And then we take the derivative of times 2x. So the 1/2 and the 2's go away. So we get x over the square root of x squared plus y squared. And we do this, it's symmetrical, x and y are symmetrical, so the partial with respect to y is going to be what? Y over square root of x squared plus y squared, j hat. And we're going to take the dot product of that with v over the length of v, of our unit vector in the direction that we want to travel. So the magnitude of, what's the magnitude of v? What's the magnitude of this vector going to be? One side of the triangle is 3, one side of the triangle is 4. 5, there we go. So the magnitude of v is 5. So our unit vector is going to be 3/5 I hat minus 4/5 j hat. So our directional derivative in the direction of u, of g, is going to be 3/5 times x over square root of x squared plus y squared minus 4/5, taking my dot product, y over the square root of x squared plus y squared. And then we calculate that at our point 3, 4. We're asking about the directional derivative at 3, 4. We plug in 3 and 4 for x and y and calculate. We get that this equals negative 7/25. We calculate that out. So what this tells us is that at the point 3, 4 on this surface, the surface is changing by, the height of our surface, z, is changing by negative 7/25 units for every unit that we move in the direction of 3i minus 4j. We're moving in the direction of 3i minus 4j. We change in height negative 7/25 units for every unit that we move in the direction of this vector. That's what our directional derivative tells us. Our function is changing. Z is changing by negative 7/25 units for every unit we move in the direction of that vector. What's that? At point 3, 4. At a different point, it's going to be different. All right, questions on the procedure that we used on that problem. So directional derivative tells us how rapidly our function is changing, our z value is changing for every unit we move in the direction of an arbitrary unit vector. We can calculate our directional derivative by using this gradient vector. And we'll do more work with the gradient vector. I'm going to talk about some properties of the gradient vector. quickly before the end of class. For the next section, we'll do some proofs of these properties and tell how the gradient vector, how other ways that we're going to use the gradient vector. It's a very, very useful vector that we're going to use a lot. So, what the directional derivative is telling us is the rate of change of the function in the direction of a specific unit vector. All right, so let me talk about the properties of the gradient. We're going to go into a little more detail with the gradient next time. For now, we're going to mainly use it to calculate, for this section, calculate directional derivatives. All right, so our properties. Properties of our direction of the gradient. So we're assuming that our function f of xy is differentiable at our point. If our gradient is 0, then our directional derivative is 0 for any unit vector. So if our gradient is 0, then our directional derivative is 0 no matter which direction we're moving. Del f gives us the direction, it points in the direction of the maximum increase of f. So our gradient points in the direction of the maximum increase. So if we're at a particular point on the surface, the gradient vector is going to point the direction, the compass heading, that would give us the steepest slope up the hill, basically. And the magnitude of del f, right, is the maximum value of the directional derivative. So we find the magnitude of our gradient. That tells us the magnitude of the greatest increase of the directional, the magnitude of the greatest increase, the greatest directional derivative. The magnitude of the gradient tells us the maximum value of the directional derivative. That's the greatest rate of increase of our function. And then we can turn that around. Negative del f points in the direction of the minimum increase. And the minimum value of the directional derivative is the negative of the magnitude of the directional derivative. So if we find the gradient and we put a minus sign in front of it, that's going to point in the steepest route downhill on our surface. The minimum increase is the maximum decrease. So it's pointing the steepest route downhill. And the magnitude of that maximum decrease is the opposite of the magnitude of the gradient. I will do the proofs of these properties are really easy, and it helps us to understand what we're talking about. But the important thing here is that the magnitude of the gradient tells us the maximum directional derivative, and the gradient points in the direction of the maximum increase in our function. So it's like a compass heading. If I go this direction, I'm going to go steepest up the hill. If I go exactly the opposite direction, I'm going to go steepest down the hill. So that's what our gradient, that's what these properties of our gradient are telling us. All right, so kind of a brand new topic, kind of a lot to digest. It's not really complicated. We will spend some more time talking about it on Tuesday, and we'll use the gradient for lots of different things as we move on. All right. Homework.